Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Next speaker is Janardhan Kulkarni, who will tell us about price of anarchy, price of independent decision making via duality.
Thanks, you all. So this is based on my papers with Sayan Bhattacharya, Sungjay Mayam, and Kamesh Munagala and Wahab Mirakni. There was a series of papers where this technique was used to bound the price of anarchy. I'm not going to talk about any specific result here, but I'm going to tell you about the technique, which is the essence of all these results. Okay? Just to motivate, selfish behavior, understanding selfish behavior is one of the main research directions in game theory. And a typical example given is, think about routing traffic in large networks. There won't be any centralized entity which can make the decisions on how to route the traffic. So it is left to the users to decide how to navigate in this network. And typically users are self-interested and they choose the routes which optimize their own objective functions, or they want to reach the destination as quickly as possible. Now the question is how these systems behave like in this selfish settings. And I'm an algorithm designer, and increasingly this question is becoming relevant for many of the algorithms we design, not just these kind of systems. Because the algorithms we design now are being used by other users, and hence the input itself can be very strategic. For example, something naive like page rank or something like ad allocations, these algorithms are used by the users who are self-interested, and they can actually manipulate these algorithms for their own benefits. So the question of understanding how these algorithms behave in selfish setting is of increasing importance in the recent works. Okay, and one of the fundamental questions which is focused on algorithmic game theory is quantifying the efficiency loss due to the selfish behavior. Like if users are behaving in a selfish way, what is the efficiency loss compared to an optimal algorithm which could have assigned users to a particular strategies? Then what will be the outcome of such system, and compare against the efficiency loss due to this. Okay, and in particular in today's talk I'm going to show how to use linear and convex programming duality to bound this quantity of the efficiency loss. Okay, so that's the main goal. Just to set the expectations right, I'm not going to talk about any new result. I'm going to illustrate this technique on something which is already well understood in the literature. In fact, everything that needs to be known on this problem is already known. But only the technique I'm going to present is something new, and I think it is interesting in its own right. Okay, so what is the problem I'm going to talk about? I'm going to look at congestion games, which is perhaps the most important problem studied in algorithmic game theory, at least in this price of anarchy literature. Like the entire evolution of price of anarchy literature can be traced to the study of this problem. And the problem is surprisingly very simple, or at least the variant of the problem I'm going to present is very simple. We are given a network and a set of users, and every user wants to go from some source to some destination. Here the user A wants to go from U to T, there is a single edge. The user B wants to go from V to T. Okay, so this is and this graph is given. These are the users, and the users can choose any path they want. So this is usually called as the strategy space. If you fix the user B, he has two choices of the paths to reach his destination. He can either take the top one or he can take the bottom one. So every user has a set of choices. Okay, but depending upon how people choose their paths, they incur some cost. In this model, it's called latency, and the latency of an edge is basically the number of users using this edge. Okay, so in this case, for example, if A decided to use the edge E, then the latency on that edge is 2 because both users A and B are using the same edge. So they incur a cost of 2 on that particular edge. Okay, and what is the player cost? What is the objective which every user is trying to optimize? He is going to optimize the latency he sees along each of these paths. Okay, and the reason why these latency functions are interesting, there is a lot of theory in it, but I'm not going to get into those details. So the cost incurred by a player if he chooses some path I is just the latency of that edge, sum of latencies along each of these edges. Okay, so that's the player cost. And so let's see on this example, here the latency seen by player B is 1 on the first edge and 2 on the second edge because both the users are using the same edge. Okay, so his cost is 3. On the other hand, the cost of player A is 2 because he's only using the first edge, that's all is, and the latency on that edge is 2. Okay, so let me see whether I can use this interactive thing. Pen and okay, cool. So that latency on that edge is 2. Okay, and what is the system designer's objective? System designer's objective is to minimize the social cost, which is sum of the player costs. Okay, so that's the objective of the system designer. He wants to design systems where every user sees a very little latency, right? So in this case, again in this example, the social cost is 5 because the user B sees a latency of 3 and user A sees a latency of 2. Okay, and now to understand selfish behavior, we have to make some assumptions on how the system behave, and perhaps the most common assumption or widely studied assumption is that of Nash equilibrium. We believe that when players behave in a strategic way, they all reach a Nash equilibrium. And what is the definition of the Nash equilibrium is that, at least the pure strategy Nash equilibrium is that if no player can decrease his cost by unilateral deviation. Okay, let me make this definition precise by just illustrating on this example. I'm going to claim that this outcome is a Nash equilibrium because the player, let's focus on player A. Suppose he wants to switch to some other strategy, and I'm going to show that that's only is going to increase his cost. Why? Because he is using this edge. Currently, he's using this edge going through this, and he's incurring a cost of 2. Suppose he switches to some other path like this, right? So that path is really long because he's going to have a latency of 2 here, 1 here, so that's basically like 5 or 6. Okay, so now he's incurring a latency of 2, but if he switches to any other path, his latency will be much higher. So we can also verify that for player B, it is his best strategy given this outcome. So this is in fact a Nash equilibrium. Okay.
Sort of equally.
Yes.
Get together,
sure. So there is another. If you had chosen another path, it would still be a Nash equilibrium. Yeah. But this is one particular outcome which is a Nash equilibrium. Okay. And the way we quantify the efficiency loss due to selfish behavior is this very nice algorithmic concept called price of anarchy, which says you take the maximum or the worst case ratio of cost of Nash equilibrium and compare it against the optimal strategy for minimizing the social cost. So there is an underlying optimization objective here where I just want to minimize the social cost. I don't want to worry about being in the Nash equilibrium. So there is some solution. Let's call it as opt. Now, since players are behaving in a strategic way, they will reach some Nash equilibrium. So I'm going to look over all possible Nash equilibrium and bound this ratio. And the reason why we care about the worst is that if you are a system designer, you can sleep peacefully because I know that every Nash equilibrium is like, pretty close to optimum. Okay. And of course, we want to understand what is the price of anarchy of games. Okay. So now we already saw that this is a Nash equilibrium and the social cost is 5. Let's see what can be an optimum solution. I'm not going to give an example what is an optimum solution, but let's see some other outcome where player A sticks to his original path, but player B now, instead of using the edge, this path which we were seen earlier, switches to this path. So now the latency seen by both the players decreases because the player A now sees the latency of 1 here, and player B on the other hand sees a latency of 3, right? So the social cost is 4. So this is an outcome which strictly gives you a lesser latency. So in fact, for this example itself, the price of anarchy is at least 5/4, because we saw an equilibrium outcome where the price of anarchy was 5. Now it is 4. Okay. And now there are also generalizations of the Nash equilibrium. For example, mixed Nash equilibrium where your strategy can be distribution over your strategies, or correlated equilibrium, coarse correlated equilibrium, and so on and so forth. And one of the nice things about these generalizations is that pure Nash equilibrium may not exist for all games, mixed Nash equilibrium always exists but cannot be computed in polynomial time, but the rest of the things can be computed, and even the coarse correlated equilibrium can even be learned through games. So these generalizations of the Nash equilibrium have very nice properties. And one of the fundamental questions I'm interested in is there a generic technique to bound the price of anarchy for these various equilibrium notions? Right? So is there a common technique which we can use? Like a lot of techniques have been developed in the literature, but is there some unifying techniques for bounding the price of anarchy? And one such technique is the smoothness framework by Tim Refgarden, which basically shows inequality of the type of the following nature. I'm not going to get into the details of this. It basically boils down to establishing some linear inequalities, and then if you can show that for this game these inequalities are satisfied, then the price of anarchy is bounded by lambda and mu. Okay, let's not get into the details. So in my view, I think this is on some sort of a potential function argument. So you have a game, you have some outcomes, and you want to design some nice potential which will gonna bound the price of anarchy. But in this talk, I'm going to show something different, which I think is equally powerful, and that's the based on idea of duality. And this is something which people in approximation and online algorithms used almost like every other proof of approximation literature uses these ideas. And what is the high level thing? The high level thing is to use the weak duality theorem. In particular, there is an underlying optimization problem. I'm going to cast it as write a linear or a convex programming relaxation of it. And we know from the duality theory that the corresponding dual linear program or the convex program, any feasible solution to the dual is a lower bound on that. And one of the like the classic the trick in approximation online literature is to connect the algorithm's cost here to some feasible dual solution, and the weak duality says that okay, this if I can bound this by some factor alpha, that's going to be an approximation factor for this, and this is something which we use in approximation algorithm literature quite often. And the takeaway for my talk is that the same trick can be used to bound the price of anarchy. Price of anarchy is still an approximation ratio, but here you are imposing the fact that you want the outcome to be Nash equilibrium. So in particular, I want to compare, I want to look at a Nash equilibrium outcome. Suppose this is some Nash equilibrium outcome, and I want to use this Nash equilibrium condition and produce a dual certificate. And I want to show that by doing this, I'm only losing some factor of alpha, and that would give me the price of anarchy. It's very similar to what people have used in the approximation and online algorithm. Okay, so this is the overall goal of the talk. So I'm going to show this, how to do this using one concrete example of the congestion games. Okay, is the high level picture clear? So that's the thing. So let's start with writing the linear. In this case, I can't write a linear program, but we can write a convex program. Let's see what it is. So just before I write the convex program, let me make some small observation. Have any questions?
This is only for lower bounds, for price of anarchy?
It's upper bound.
It's upper bound, because you need to look at the worst Nash equilibrium.
Yeah. So I mean, I'm not even gonna assume what is this Nash equilibrium. I'm gonna just look at some Nash equilibrium, and I'm gonna produce a dual certificate which satisfies. I'm gonna show a dual feasible solution using that. So I'm not making any assumption on whether it is the best or worst or anything. It can be any Nash equilibrium as long as the outcome is in. So which in particular means that if this was the Nash equilibrium with the highest cost, I'm going to bound that also.
This is the problem with the English word any. So you mean every.
Okay, for every Nash equilibrium. In particular, I'm not bounding the price of stability. I'm in fact bounding the price of anarchy. Okay, so to help me write the convex program, let's make some small observation which is very simple. So I can write the social cost, which was sum of the player costs, as simply latencies on the square of the latency on each edge. Because if you fix an edge E that is being counted among all the players, and the latency was equal to the number of the players, so the social cost is basically the latency squared. Okay, so this is a simple thing. So let's write the convex program. In the convex program, I have two variables, xij, which basically says the player j takes the path I in the graph. Okay, and there is a variable ye which basically measures the latency of this edge. Okay, and I need this parameter li, which is length of path I. This is not a variable, this is just some constant. For every path I, li measures the length of this path. Okay, so then the objective, okay, here min is short for minimize. Okay, it's not a so objective is basically ye squared, because that's my social cost. So this measures the latency squared, and here I need this extra term. For this talk I will just briefly sketch why I need this extra term. So without this linear program has a large integrality gap. Think about only one player and n paths, and then without this the li term, the cost will be 1 over n squared, which is not really true, because the player has to choose at least one path, so his cost is at least 1. So the way to fix it is, if a player I chooses the path, player j chooses the path I, he has to pay at least li, the length of the path, because he's at least one user using that path. Okay, so if it is not clear, then we will not going to bother too much. It's just we need it to fix the integrality gap of this convex program. But the objective is quite simple. This is basically ye squared, which is what my social cost is telling.
In the original formulation, does the length of the path figure in the cost? You have the length time. Oh, this is the length of the total.
Yeah. So this anyway is the lower bound on the. Yeah.
But just to make sure I understand, so you're allowed to divide between all sorts of different paths.
No. So that is splittable. In that case, I don't need this. That's a good point. Like if I was allowed to split, choose like fractionally choose the paths, then I don't need this term. That would have all that ye squared is all that I would have needed. But here in this, what I'm talking is you to choose one of the paths integrally. Okay.
So this is specific for this specific latency function on the edges. Does it generalize?
It generalizes. I'm going to show at the end of the talk. Like it generalizes to many problems. Yeah.
Can you just rephrase again why you need the second term in the objective?
Okay, so let's take one concrete example. There is a path with n edges, n parallel edges, and there is only one player who wants to use this graph. Okay, if I only put the first edge, the linear program is going to say take 1 over n, where I'm going to take each edge to an extent of 1 over n. Okay, my objective is going to be 1 over n squared, but the player incurs at least a cost of 1.
Wait, it's going to be 1 over n. You're summing.
Okay, 1 over.
1 over n.
Yeah.
N times squared.
Okay, if there were multiple players, then.
No, it's fine.
Yeah, it's fine. Yeah.
1 over n, but it should be 1.
Right. So, but on the other hand, since he is using at least one edge, he has to pay a cost of 1, right? So that's what this term is fixing. So he's saying if I took the path I, right, I'm going to pay at least 1 along each edge, whether there is other players in the system or not. That's how I'm going to pay, and so that's I'm saying that is li, right?
So that's, I mean, so you're thinking of a linear program relaxation, and xij is going to take value 0 or 1 for each path.
Yes.
But that's in a model where you could take several different paths.
I want xij to be 0, 1, but I can't solve that version. So I'm going to relax it to be a linear convex program. So there it can take fractional values.
So in the integer case, this right-hand side
is equal.
The lower bound
Yes.
is less than the left-hand side, but
Yes. Yes.
But in the fractional case, it can be bigger, so you can safely speak.
Yes. Yes.
So really, it shouldn't be ye squared. It should have been ye times the number of people who use it. But if they were integers, then it was squared. That's the point. The fractional, they're not.
Yeah.
It's the product of those two.
Right. Exactly. Okay. Is it clear?
Yeah.
Yeah.
Thank you.
Okay, so what are the constraints? Constraints are fairly obvious. So xij means that player j is using this path I, so there are multiple choices of paths he has. He has to take one of these. Okay, so xij is just 1. Summation over all I, it has to be 1. So which basically says every player chooses a path. Okay, and then what is the second constraint? The second constraint is going to say that the latency on edge is at least the number of players using that edge, which is basically summation over all I and summation over all j xij, where path I uses this edge E. Okay, so this is all over all paths which use the edge E. Suppose there are multiple paths going like this, you fix an edge E, then that's the summation over all of that, and xij is the whether player j is using the edge I or not. Okay, so y has to be at least this quantity.
I still am confused about have 1. So I is an edge in 1. We're summing over edges.
No, I is just all possible paths he can take. The player J can take.
But it's
I index is path.
okay.
Yeah. I index of a path. So this graph is given to you. Okay. So the convex program is fairly obvious. I mean, so there are no special tricks except the fixing the integrality gap of that. Okay. So now, so this is a convex program. This is not a linear program, and the people who are not familiar with how to write the dual of this, I'm not getting into the details. There is a very nice survey by Nikhil Devanur, who is not here. You can see how to write the dual of these linear programs. Okay, I mean, in a way that you can separate the constraints from the objective, which is something similar to the LP duals. So here, the dual gives me, the dual is something like this. It says it gives a variable j, alpha j for every player, and it gives a variable beta e for every edge. Okay. And so that's the objective. This is all obtained using standard taking the LP duals. There is nothing deep going on here. But let's understand these constraints. This is where this will be very crucial for price of anarchy analysis. What is this constraint trying to tell me? So the constraint is telling if you fix, so the dual is going to give me one variable for every edge, and there is a constraint for every player and every set of possible paths for every pair ji. So in particular, if you fix a player j, so this constraint says that alpha j has to be less than all possible beta e plus li. In particular, it has to be less than minimum or all possible edges e, right? Maybe the player is going to take this path, or maybe the player is going to take this path. Corresponding to every path, there is a constraint, and what the dual is telling me, this alpha j, whatever may be the value of this alpha j, it has to be less, minimum of these two quantities. Okay? So let me rewrite this. This is what this dual is telling me. So the alpha j in the dual solution has to be minimum over all the constraints I had corresponding to the player. And this is very similar to what Nash equilibrium is trying to tell. Nash equilibrium is telling that in the Nash equilibrium outcome, the cost of the player has to be minimum over all the strategies he had. Like if he deviates unilaterally his cost, the cost he incurs has to be minimum of these quantities, right? So this is what dual constraint told me, and this is what Nash equilibrium is telling me, and perhaps there is a connection, right? I mean, this pattern we cannot miss. So maybe this beta e plus li, this quantity, I want to interpret as the cost of player using this strategy I. So in essentially, that's what I want to show. So in particular, I'm going to define alpha j as the cost player incurs in the Nash equilibrium theta, and beta e to be the latency on this edge e. So there is some outcome. This is a Nash equilibrium. I'm not making any assumptions on this Nash equilibrium. And player j incurs some cost. Just define alpha j to be that quantity. And in this outcome, beta e is the latency on this edge. Okay. So what happens if I define like this? A particular note that the cost of j, the cost incurred by player j is going to be minimum over all this because of the condition of the Nash equilibrium. And this immediately gives me some bound on the price of anarchy just by the definition. Because what is the dual objective? Dual objective is summation over all player costs minus beta e squared. And by the definition, I defined alpha j to be the cost of the player in the Nash equilibrium. So the first term is just the cost of the Nash equilibrium. And the second term beta e squared again is the cost of the Nash equilibrium because I defined beta e to be the latency. And this in fact gives me the dual objective is at least 3/4 the cost of the Nash equilibrium, 3 over 4, and which means the primal objective is at least this, and this will give me a bound of 4/3, right? And in fact, if someone asked me whether the players can choose fractionally, in fact, if the player chose fractionally, this in fact would have given me the bound of 4/3 on the price of anarchy, which is tight in fact. But since I used this Li term in the objective, in the primal objective, which means that the primal was not the tight, is not a lower bound on the opt, you lost some factor there. So if you take into that account, then you will get the price of anarchy. Okay, I'm not going to do that, but it gives the tight bound known for this problem. Okay, how much more time I have? Okay, so I think I don't know why it doesn't show the time here. Okay, so I'm almost done. So I'm left with doing only one thing to show that the constraints are satisfied. And let's just verify for one case. So why is this constraint satisfied? So the alpha j, it is fairly obvious, because alpha j is basically has to be less than beta e plus li, and the way I have defined beta e is just the cost of using this edge, and that in fact that's what I set alpha j to be the cost of the player, and the beta e is just the cost of using this edge, and that's by definition satisfy the constraints. Right? Okay, for if the player switches, then I have to argue that the cost of each edge increases by at most 1, and that's where this quantity Li saves me. Okay, but this is just by definition these constraints are satisfied. Okay, so and now to bound to the more general concepts of equilibrium, instead of setting the cost, you set in the expectation. If the distribution is in coarse correlated equilibrium, you take the expectation of these quantities and entire proof goes through. Okay. So someone asked me whether this is very specific to this problem. It's not. I could prove like all of these results and obtain the tight bounds exactly using the same proof technique. So, and in fact, there were several open problems like coordination mechanisms for temporal routing and things which were not known how to solve using smoothness framework, and we can get results using this, and these were the first results known. And at least to my understanding, I think the smoothness framework and the duality are equally powerful, although I might be wrong. And that's one of the questions worth exploring. And another thing this technique highlights is that can we use this to bound the price of stability? Like if you start with some dual feasible solution and say that I can modify this dual feasible solution in a way to bound a Nash equilibrium, converge to a Nash equilibrium, then we can also get price of stability results. Okay, so I overshoot by a couple of minutes, and that completes my talk. I will leave you with this picture of the entire framework. Thank you.
Okay, so we will do questions privately over the break. So, and we will continue in 4:20.
Suppose